All right. Hello, everyone. Welcome to class. So, actually, it's a follow-up to our discussion, which we started from the Stewart textbook, which we have been following closely since we started the class. Okay. So, in this section, we actually want to learn another series test. Okay. Remember, just to remind you, we actually already looked at integral test from 11.3. We looked at geometric series. We looked at the idea of P series from 11.2, and we looked at the test for divergence in 11.2 as well. So both in 11.3, we're going to be focused on the comparison test. Okay, this is comparison. Okay, so why did we decide to study this comparison test? Again, I want to remind you that you don't always find the sum of a series in every situation, okay? So then we have the idea of these different tests that can give us some kind of information about the series, whether it converges or whether it diverges, okay? So this test actually, again, informs us the behavior of that series. Okay, so what is the motivation? So let me just write a little bit. Motivation. Okay, the motivation is that we seek to compare. Now, just like the word comparison, the root word for the word comparison is compare. Okay, so placing two things side by side and discussing what kind of relationship exists between them, right? Okay, so and it's the same thing we're technically doing right now, to place two things side by side with themselves, and then we're going to try to discuss, their behavior or perhaps some kind of similarity. Okay, so we seek to compare a given series. Okay, now the behavior of this given series is unknown. So what do I mean by behavior? I mean, whether it converges or diverges, you don't know at the moment, okay? And that's what you're seeking to establish. You seek to compare a given series with a series that is known to be convergent or divergent, okay? So by now, you already know what type of series diverges. A simple example, harmonic series, always divergent, okay? So a very trivial example for a convergent series, you can talk about a P series where your P is 2, okay? P is, and for convergent P series, your P has to be bigger than 1, right? So, and you have a series of some of 1 over n squared. This is a very simple P series which is convergent. All right. Okay, good one. So let me tell you something, guys. So observe. Now I want to make an observation, or perhaps let me just call it observation. So I talked about motivation. Let's call this guy an observation. Okay. You have the series where your n is going from 0 to infinity. It's 3 divided by 1 plus 5 to the power of n. Now, we want to know, guys, if this series converges or diverges. Okay, so I say converge or diverge. Now, what do we do at the level of comparison tests? Okay, so what we do at the level of the comparison test, we are going to pick the AN, okay, which is 3 divided by 1 plus 5n. Now, can I compare this guy with another thing? Okay, so a quick example of, let me say, can I compare it with something else that is close to it? Okay, so I can actually compare it with 3 over 3 to the power of n. Now, I have to establish a behavior between these two guys. Is this quantity, is it less than this guy? Or is this quantity bigger than this guy? Now, sometimes what helps us determine that by listing the terms. Okay, so let me just show you guys a very simple one. So when n is 1, what happens? So you have a 3 divided by 1 plus 5 to the power of 1, right? Which is 3/6, and this is exactly 1/2. All right. So, but for this guy, when n is 1, so let me do it this way. What happens? You have a 3 divided by 5. Now, 1/2 is just 0.5. 3/5 is 0.6. That's when n equals 1, right? When you do n equals 2, when n equals 2, what happens? You have a 3 divided by 26. And over here, when n equals 2, this is 3/5n. This is what we're investigating here. Over here, we're investigating 3 divided by 1 plus 5n, right? 5 to the power of n. When n equals 2, this is 3/25. Now, what can I see, guys? It's easy for me to see that this 0.5 is actually less than this guy. 3 divided by 26 is less than this guy. So that gives me an idea of their relationship. That as I continue to increase n from 1 to 2, blah, 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 this guy is going to be less than this guy. Okay. Now, what is 3 divided by 5 to the power of n? Can I rewrite this guy? Okay, yes, I can actually write this guy as 3 multiplied by 1/5 to the power of n. Okay. That's no big deal, guys. Okay, so it's straightforward because you can split that guy by algebra. Okay. Now, can I give you guys some information about this guy? Okay. So I need to tell you guys that this guy, just exactly what we did right here, I'm going to write it in words. So this guy here, so I'm going to say this guy, this has smaller terms. So smaller terms than this guy. Okay. This guy has smaller terms than this guy. Now, but what do we know, guys? If I write, okay, so now if this happens, that means I can write it in terms of the series. So that means in terms of their series now, this guy, n plus 5 to the power of n, would actually be less than this guy. Okay, but what do we know, guys? What is this guy called? Okay, what is this series called? Okay, I'm taking it a little bit slow. Okay, this guy is actually called a geometric series. Okay, remember that? So now, what have I succeeded in doing? I've succeeded in comparing a given series with a geometric series. Okay, so now let's see. Now, the given series, this guy over here, the convergence or divergence of this guy depends on this guy. Okay, if this guy converges, then that means this guy converge. If this guy right here diverges, then okay. Okay, so let's see. Okay, let's move on. Okay, so for this geometric series, what do we know, guys? What do we know? Okay, we know the R is 1/5. And we know the A is 3. Okay, does this converge? I only need to check if this guy is less than 1. Okay, so this is 1/5, which is still 1/5, which is less than 1. Absolutely, convergence. Okay, convergence. And if this is a geometric series, it converges, can I find the sum? Definitely. A divided by 1 minus R. What is A? 3. 1 minus 1/5. So this is like 3 divided by 5/5 minus 1/5. So pretty much, do we have we have here for ourselves 3 divided by 4 over 5. And this is exactly what? 15 over 4. Now we've been able to find the sum. What is going to be our conclusion? Okay, so conclusion is going to be that, of course, I know that this guy, right, this guy here, is convergent. Okay, so of course this is just a geometric series, convergent geometric series with sum 15 over 4. Okay, so to put that in a mathematical perspective, what do I write? I'm going to write this guy n from 0 and from 0 to infinity of 3 divided by 1 plus 5 to the power of n, which is less than this guy. So I'm just copying pretty much what I have on top. I'm just copying it and putting it back here. Okay, what is this sum equal to? This guy equals 15 over 14. And thus, this guy is convergent. Now, can I walk you through what we just did in just a couple of seconds? Okay, so what did we do? We have a given series, this guy, okay? So now we need to determine if it converges or diverges, right? So right now you cannot do TFD. If you don't want to do TFD, you can do something else, okay? In this case now, if you do TFD, it's not going to work, right? It's going to fail. Okay, so you have cases where when you do TFD or when you do some kind of series test, it fails. So, or perhaps we'll say it's inconclusive. Okay, so you have to try something different. So once we have this given series, the goal is to compare it with a known convergent or divergent series. And what's the first comparison we can make? 3 divided by 1 plus 5 to the power of n is actually less than 3 divided by 5 to the power of n. And by the time I put in my summation sign, I see that we have this kind of inequality, where on my right-hand side, I have a geometric series. Being a geometric series, I can be able to determine if it converges or diverges. Okay, so, and I'm lucky in this case that my geometric series actually converges. Okay, so since it does converge, I can then conclude that the given series or the original series is actually convergent. Okay. All right, good. So now let's now formally write the statement of the comparison test formally. Okay. So let me say the comparison test. Okay, so take note of the statement of the test. It's important, guys. So let us have a series AN and B, series of AN and BN. Let this guy be series with positive terms. Okay, so you got to be careful and take note of what each test actually represents. So let this guy be series with positive terms. Number one, if the series of Bn is convergent, okay, and if An is less than or equal to Bn for all values of n. So guys, it has to be for all values of n and not for some values. Then what do we conclude? This guy is convergent. Okay, that guy is actually convergent. So now I need to write something in red just to help you guys. Now the terms of this AN, right? Let me just write terms. Okay, so terms of AN are smaller than those of a convergent series. Now, when we have this structure as described, okay, so when we have this sort of structure, the terms of this AN are actually smaller than those of a convergent series, just like the example we did right on top, okay? So number 2 is if the series of Bn, now we've talked about when it converges, what about diverges? When this guy is divergent, what happens? And we have a reverse inequality, okay? For number 1, we had less than or equal to. For number 2, we have a greater than or equal to. So if it is divergent and that happens, again, it has to be for all values of n. That means when n is 1, n is 2, n is 3, you know, on and on. Okay, so then what do we actually conclude? The series of AN is divergent. Okay, so similar to what I wrote in red, so let me write something again in red. Okay, so let me say in this case, terms. The terms here are larger, okay? The terms here are larger than those of a divergent series. These terms are actually larger than those of a divergent series. Okay. Now, can I just give you guys, something that is going to be helpful? So to use this, we actually need a good series. Okay, what do we mean by a good series? Pretty much like a standard series that is either known to converge or diverge to compare against. As the name says, comparison. Okay, so most often we can use the P series. How does this P series look like? You have this guy. Okay, when does it converge? Convergent if your P is bigger than 1, right? And when does it diverge? It actually diverges if your P is less than or equal to 1. Okay, so another one we can actually use is the geometric series. Okay, so these are common ones. That doesn't mean that's the only thing we can do, but these are very common. They are actually often used. Again, they are not the only thing you can use, but oftentimes these are the commonest. Okay, so this guy diverges. Okay, so now at this moment we are good to do some very beautiful examples that can really help us. Okay, now example. Okay, so if I have a series, example 1, this is n from 1 to infinity. You have a cosine squared of n divided by n squared plus 1. Obviously, I cannot use my TFD. I cannot likely use my geometric series at this point. No, so I have to think about what to do. Hence the comparison test. Okay, so solution. So I'm going to pick the nth term, which is cosine squared of n divided by n squared plus 1. I need to make a comparison. Okay, so you have to think about a quantity that is bigger than this guy. You got to think about a quantity that is bigger than this guy. Let me use examples, right? Let me use numbers. I give you a number, say 1. and I say, give me a number that is bigger than 1, then you say 2, then 1 is less than 2, okay? So in this case now, you have this quantity. I need a quantity that is bigger than this guy. Now, sometimes for trigonometric functions, they are even interesting because you can play around their properties. What do I know? I know cosine of any number is between 1 and -1, right? But in this case, we'll just pick the positive part, right? Because if you pick the negative part, then this guy is going to be bigger than that guy, okay? You can just pick 1. So I pick a 1 here, divided by n squared plus 1. Of course, this guy's less than or equal to. Okay, you see the first step, you got to think about a guy that is bigger than cosine squared of n divided by n squared plus 1, right? So again, I cannot actually stop here because there's nothing that this is going to give me really based on everything we've learned so far, okay? So as we move on into the future, you can even think about something else. If you have this kind of series, what can be done, okay? So we're trying to stay on track based on what we've learned so far. So I need to again sometimes you make more than one comparison, okay? That's fine. I need to compare this guy with something else. So your comparison has to be like, it has to follow a logical flow. Okay, so you cannot just say, oh, I'm comparing this guy. Okay, let me tell you what, some students can do that can be so wrong. Just say, oh, this guy is less than or equal to 1 over n. I mean, this is not true. This is not true. Okay, so you see the logical way we're trying to drive this to a conclusion. So this quantity, I need something that is bigger than this guy. What can I think about? 1 over n squared, less than or equal to. And if you really want to be sure that these guys are correct, you can test them with numbers. If you test them with numbers, you see they are true. Okay, so if this is true, what can I do, guys? So this means that if you put a series, this is cosine squared of n divided by n squared plus 1, right? It's less than or equal to the series over here, right? So I'm just applying my sigma notation. But really, this is the given series. I'm going to draw a line between this guy, okay? Now, to say that, what do I mean? So this is what I actually mean. This guy, this is cosine squared of n divided by n squared plus 1. This is less than or equal to this guy. Now, at this point, we have to think about this series. What's the behavior of this series? Does it converge or diverge? Okay, so this guy is a P series, right? Where P equals 2. 2 is greater than 1, that means it converges. Okay, so what's going to be my conclusion? Remember, let's go back to the statement of comparison test. If the series of Bn, this is the Bn, the guy on the right-hand side, if it converges, then the series of the guy on the left-hand side converge. So let's see. This is the series of the guy on the right-hand side. It does converge. What is going to happen to the series of the guy on the left-hand side? It will converge. Okay, so conclusion, I'm going to say that this guy converges by what? By comparison tests. Okay, so let me write it this way. Comparison test. Okay, so if you don't want to write it like this, you can decide to write it in another way. Okay, so you can decide to say this guy converges by comparing with that series. Okay, so guys, it's important actually to state this guy. Okay, you got to give us the reason why the series on your right hand side converges. It converges because it's a P series and P equals 2, 2 is greater than 1, so it converges. Okay? Okay. So if I want to write what I just said, I'll just say since this guy is a P series with P equals 2 and it is convergent. All right? Make sense, guys? All right, cool. Now another example, example 2. In this case now, suppose we have n goes from 1 to infinity, 6 to the power of n over 5n minus 1. Does this guy converge or diverge? So we're asking the same question, okay? Remember, in this session, the only thing we want to do is use comparison tests. That's the only thing we really want to do. Okay, so again, I'm going to pick the nth term, 6 to the power of n divided by 5n minus 1. I need to compare this quantity with something that it's either less than or bigger than. Okay, so you can start very basically by saying, okay, when n is 1, what happens? Let me see the behavior of this guy. I'm going to have a 6 divided by 4. And that is like a 3/2. Interesting. So I need something that is going to give me a quantity either bigger than 3/2 or less than it. But again, you have to stick with these guys. Your logical conclusion or your reasoning has to be within the n term you're given. I got 6 to the n on the top, 5 to the n on the bottom. 6 to the n on the top is the largest. Okay, so I'm going to retain it. Right? So on the bottom, what is the largest? 5 to the power of n. This is 5 to the power of n. Now, when n is 1, for this case, I'm going to have a 6 to the power of 1 divided by 5 to the power of 1, right? And that's a 6 over 5. 6 over 5 and 3 over 2. Which one is bigger? Okay. 3 over 2 is actually bigger. Okay, so this guy is going to be greater than. And this is going to be, now you have n on the top, n on the bottom with the powers. Okay, remember how you're doing this is, right? Got something like this. Now, can I actually make sense of this? Sometimes you got to do some manipulation. This kind of looks like the geometric series, right? This looks like the geometric series. But remember, it's going to be perfectly fitted. Now, remember when for geometric series, you got to pay attention to this indexing. Over here, n starts from 1. Your geometric series, when n starts from 1, has to be written in this manner, right? But look at this guy. This guy is just n. So I got to think about a way to introduce this -1. And watch this trick, guys. This is the trick. This is going to be, you're going to have a 6 over 5 times 6 over 5 to the n minus 1. Think about this, guys. Okay, pretty much nothing really, right? If you do a 2 divided by 2, it's still 1, right? If you do 2 divided by 2 times 1 million, it doesn't change 1 million, right? And that's exactly the same thing we did right here. Think about this. We did something like 6 over 5 times 5 over 6. This is 6 over 5 times. Now, I want to flip this guy. This becomes a 6 over 5 to the power of -1. And then you have 6 to the power of 5, 6 divided by 5, I mean, to the power of n times 6 to the power of 6 minus 5 divided by, I mean, what am I saying? Okay, so this is what I'm saying, guys. You have a 6 over 5 to the power of n, right, times 6 to the power of 5 divided to the power of -1. This is exactly going to be this guy, n minus 1. So you see how we got this guy, okay? Nice. So intuitively, this is what we have, basically. Got something like this. So now I got to introduce my sigma notation. Okay, so we got to introduce the sigma notation. Okay, so pretty much the sigma notation is not going to distort the inequality. Yes. Nice. But what do we know, guys? You got to pay attention to this guy. Okay, so this is a case of an. This is a case of an greater than bn, right? So what kind of series is this? This is a geometric series. Okay. So I'm going to say this guy is a geometric series with what? What is your R? 6/5, which is bigger than 1. And once you have the situation, what do we say? It is divergent. Now, when your series of the right-hand side is divergent, what does it tell you about the series of the left-hand side? In this case, it does diverge, okay? So I'm going to conclusion. This series, which is the given series itself, is divergent by what, guys? By the comparison test. Okay, makes sense, guys? Okay, so let's do another example. In this example, we have n from 2 to infinity, 1 divided by, got n minus square root of n. Again, we're attempting to answer the question, converge or diverge. How do I go about this again? Help me out. I do an, right? One, don't just pick it out. I don't want to write it. Something like this. So I got to compare this guy with a quantity, right? As either bigger than or less than. Take a look at the top. The highest guy on the top is 1. So you retain your 1. Divided by, take a look at the bottom. What is the highest? N and square root of n. Which one is bigger? N is bigger, so you keep the bigger guy. So what's the relationship that exists between them? Is it going to be less than or greater than? Okay, this is going to be greater than. Now, how did I know? Just to do this. When n is 1, so if you're not so sure, you can use some little numbers like n equals 1 and 2. And if you have time, you can go to 3. Okay, so in n equals 2, you don't start with 1 because your indexing starts from 2. If you start with 1, there's a problem. Okay, so when you are doing this kind of testing, keep in mind your indexing. When n is 2, you have got a 1 over 2 minus square root of 2. Yeah. What about this guy? You got a 1/2. This quantity and this quantity, which one is bigger? Okay. This guy is going to be bigger than this guy. Okay. So sometimes these are things you really do because without doing them, there's no way you're going to have like a good conclusion. Make sense, guys? Okay, nice. So again, I'm going to introduce my sigma notation. N minus this guy is bigger than. Okay, talk to me, guys. Talk to me, the job is done. Okay. So what kind of series is this guy? This is harmonic, guys. Okay, so n equals 2 to infinity, 1 over n is a harmonic series. And what do we know by harmonic series? Diverges. So what's going to be my conclusion about my given series? Conclusion. We're going to say the series, the given series diverges. It's important to tell us the test you're using, okay? By comparison tests. This is even amazing, guys. All right? Okay. Let's look at another example. We're attempting to answer the same question of whether converges or diverges. Solution. What am I going to go do? Pick the n term. You add a 4 plus 3 to the n over 2 to the power of n. So what do I do? Look, take a look at the top. What is the largest? As n increases, the biggest guy on the top is 3 to the power of n. The bottom, you just have 2 to the power of n. So you need an inequality sign, whether less than or greater than. What do you guys think? Is this quantity on the left side bigger than the right side or less than? So let me tell you that for free. Quantity on the left side is bigger than the right side. How did I know? You can do exactly the same thing we've done before. Plug in n equals 1, plug in n equals 2, and then you see that clearly. So right now, I'm free to actually introduce my sigma notation. Okay, so this is n from 1 to infinity. 4 plus 3 to the power of n over 2 to the power of n. This guy is bigger than, got us something like this. Keep in mind that this guy can be written as this. All right. And similarly to what we did before, guys, I can also do that kind of exactly the same trick. This is 3 to the power of 2. 3 divided by 2, I mean, this is 3 over 2, n minus 1. So just the same example we did right on top. Let me be sure. Let me tell you the exact number. That's example 2. Exactly the same thing, guys. Exactly. Because we really want to put it in the form of the geometric series, which it is. Okay, so what do we know, guys? This guy, geometric series. My R is 3 over 2. This is bigger than 1. What do we say, guys? Diverges. Well, it's going to be my conclusion. My conclusion is that the given series, which is this guy on the left, diverges. Do I stop there? Not quite. I'm going to tell us the tests by a comparison test. Does this make sense, guys? Okay. I hope you're finding it interesting already. Okay. I hope you're finding it interesting. All right. Now let me just do one more and then we discuss the limit comparison test. Okay, so we've looked at comparison tests and we got to talk about the limit comparison test where I actually introduced the idea of limits. Okay, I'm going to bring in the idea of limit and we'll see what we'll find from there. Okay, another example, this should be example 5. And from 1 to infinity, you got a 2 plus negative 1 to the power of n divided by n squared of n. So this, it's interesting because it combines, you see negative 1 to the power of n, you see a square root sign, and it looks like, oh, what is this? I mean, take it easy, take a deep breath. We can do this, okay? So we want to check again, converge or diverge. Solution. You pick the nth term, you have a 2 plus negative 1 to the power of n divided by n squared of n. Okay, so take a look at the bottom. You have 2 here. I mean, take a look at the top, you have 2. Negative 1 to the power of n is definitely smaller than 1. Negative 1 to the power of n is smaller than 1, yes. Because when n is 1, it is negative 1. Negative 1 is smaller than 1. So in the long run, it is less than or equal to 1, pretty much. Not just smaller than 1, less than or equal to 1. Okay? Divided by, you retain this guy. Now, I need to think about the sign. Is it going to be less than or equal to? This is going to be less than or equal to, yes. This is exactly 3 over n square root of n. Let me put something in red. This guy is the one that gives us this guy. All right? Why? Because a negative 1 to the power of n is less than or equal to 1. At some points, especially when n is odd, it's less than 1. But when n is even, it's exactly equal to 1. All right, so right now I'm free to introduce my sigma notation just like before. Which is 3 divided by n. Now, this guy, what is square root of n? I can write this guy as n to the power of 1/2, right? So you have a n times n to the power of 1/2. What does this give you? N to the power of 3/2. And that's what I'm going to write here. Okay. So, but this is a series. 3 is a constant. You can pull it out. 1 over n. Talk to me, guys. What kind of series is this? Talk to me. This is a P series, okay? P series. My P is exactly 3 over 2, which is bigger than 1. What do we say, guys? Converges. So what's going to be my conclusion? If the series of the right-hand side converges, what does it tell you about the series of the left-hand side? It converges, okay? 2 plus negative 1 to the power n divided by n squared of n converges by what? Comparison test. So, but I'm going to just give you guys a note, more like a warning. When you work with things like this, take notes. If the series of an is to be tested, you got to take note of 2 things, guys. Number 1, an must be less than, okay, less than the terms of a convergent series. And if you look at what we've done so far, that's exactly the case. And our an must be bigger than what? The terms of a divergent series. Good. So now let's move on, guys, to a different one, which we call the limit comparison test. So here we're going to introduce limits, but we're still doing the comparison test essentially. Now, what is the statement of this test? Now, suppose that a series of an and the series of bn are series with positive terms. Suppose they are series with positive terms. If the limits as n goes large of an divided by bn equals c, okay? Where your c is a finite number, all right? So where your c is a finite number, essentially c is greater than 0. Then, interesting, then either both series converge or they both diverge. Okay, so let's talk about this. You have two series of AN, a series of AN, a series of BN. They're giving us positive terms. Now, if I pick their nth term, if I take the ratio of their nth term and check as n goes large, if it gives me a constant, that tells me that then this should be a then. This is then either both series converge or both series diverge. Okay, let us see, guys. Let us see how to go about this. Interesting. Okay. Now let me give you the first example I want to talk about. Example. Let's pick a simple case. It says test test the series for convergence or divergence. Okay. What do I do in this case? Solution. Now remember, there's a series of AN and there's a series of BN, right? So pick this guy first. Now look for a quantity that is either less than this guy or bigger than it. Okay, so let me give you a very easy example to deal with. I mean, easy situation to deal with. You can pick 1 here divided by, I can just pick 2n if I want. Okay, or I can just pick n. Okay, I call this guy my AN. I call this guy my BN. Now, what does this limit comparison test, which is called LCT? Okay, so let me tell the acronym LCT. What should I do right now? I'm going to do AN over BN. But I got to consider the limit as n goes large. So we do limit as n goes large. What is AN? You got a 1 over 2n plus 3 divided by, what is the limit of BN? You got an n. So if I try to work with this guy, I'm going to have a limit as n goes large, n divided by 2n plus 3. Okay, so how do you find this kind of limit? This is n over n, 2n divided by n plus 3 divided by n. So this is limits as n goes large, you got a 1 on top. This is 2 plus 3 over n. Talk to me, guys. What's this limit? 1/2. Okay, so what kind of number is 1/2? This guy is greater than 0. Okay, that guy is exactly greater than 0. Okay, so if it is greater than 0, the conclusion is that both series diverges. Makes sense, guys? Why does it diverge? Somebody has a question. Okay, you just got a number bigger than 0. Why does it diverge? Simple, guys. That's because my series of Bn is a harmonic series. Okay, so because it's a harmonic series, life becomes easy. Okay, so keep in mind that this guy, harmonic. This guy is harmonic series does what? Diverge. So this is a kind of the limit LCT, which is the limit comparison test, is a more integrated form of the comparison test. So you see, the only thing we're not doing here is to determine what the relationship is, whether less than or bigger or equal to. The only thing, we're not just putting it, okay? But we're trying to pick like the biggest term on the top and on the bottom, okay? Now let's look at another example. N from 1 to infinity, n squared minus 5n divided by n cubed plus n plus 1. How do I go about this one? So again, we want to test for convergence or divergence. I'm going to pick this guy, n squared minus 5n divided by n cubed plus n plus 1. This is my an, series of an, the original guy. How do I know the series of bn? You take a look at your an. What is the largest thing on the top? The largest thing on the top is n squared. What is the largest thing on the bottom, or the largest quantity? Okay, the largest quantity on the bottom is n cubed. Can I simplify this guy? This is 1 over n. Okay, so let me write this guy in this manner so that you guys can see what I did logically. So this is an equals, this is bn equals 1 over n. So in this case, it doesn't matter if I do 1 over 2n, okay? It's going to be the same conclusion. If I do 1 over 2n, the only thing is that I'm going to have a 1 over 2 up front, but you still have a harmonic series, so it doesn't make a difference, all right? Okay, so by limit comparison tests, this is what I need to do. Okay, so both series diverges by what's LCT, so I need to fix that. An divided by bn. So this is limit as n goes large, n squared minus 5n over n cubed plus n plus 1 divided by 1 over n. This guy is limit as n goes large. You gotta have n right here, n squared minus 5n all over n cubed plus n plus 1. So what do? I can distribute the guy on the top. I have an n cubed minus 5n squared all divided by n cubed plus n plus 1. Does it look interesting, guys? So you need to find this limit right now. What do? You divide by the highest power of n, both on the top and the bottom, okay? So pretty much this is not a limit class though, but I try to, break things down, make it a lot easier in case you're a little bit rusty when it comes to dealing with limits. So this is the limit as n goes large. You got a 1 on top here. You got a minus 5 over n. You got a 1 plus 1 over n squared plus 1 over n cubed. So what is this limit essentially? This is a 1. 1 is greater than 0. Now, what is going to be my conclusion again? Conclusion is based off what is the take a look at the series of bn. What's the series of bn? Harmonic. Again, it's harmonic. Okay, so what do I conclude? Conclusion. The series diverges by the limit comparison tests. You have to pay attention to the series of bn, this guy, again, harmonic, again, diverges. So, so far everything we're doing is like, does it always diverge? Can't we have a case where it does converge? Yes, we would have a case like that. And that's going to be the last example I'm actually going to talk about here concerning the LCT. So again, I'm given this series 1 over 2 to the power of n minus 1. I want to test for convergence or divergence, okay? Solution. Again, here we're using the LCT, which is a limit comparison test. What is my AN? My AN is the original guy that is given, okay? What is my, okay, I missed a negative 1. How do I find my Bn? Take a look at the top. What's the highest guy? Just 1. Take a look at the bottom. What's the highest quantity? 2 to the power of n. But keep in mind that the series of Bn itself, the series of this guy, is going to converge. Okay? Because it's a geometric series, I can transform this guy. Got a 1/2 n minus 1. Okay? I can transform it in that manner. And this guy, of course, is geometric. Your r is 1/2 is less than 1, converges. Okay, so that is right there in my mind, right? So that's going to guide me to what I need. The limit as n goes large of an divided by bn. What is an? Limit as n goes large, you got a 1 over 2 to the n minus 1, all divided by 1 over 2 to the n. Can we do some simplification? Obviously, limit as n goes large, you got a 2 to the n on top, divided by 2 to the n minus 1. How do I handle this? Again, divided by the highest quantity, both on the top and on the bottom, minus 1 over 2 to the n. Almost there, guys. Limit as n goes large. On the top, I have a 1 right now. 1 minus 1 over 2 to the n. As n goes large, guys, what happens? This guy gets to 0. So this limit is 1, and 1 is bigger than 0. So what is going to be my conclusion? I can say that since the limit exists, okay, so this last example, this is a formal way to write these things. Okay, so since the limit exists and this guy is convergent, then the series is convergent by what, guys? LCT. What is LCT? Limit comparison tests. Okay, so guys, that's going to be a wrap for 11.4, which focuses on both, focuses pretty much on the comparison tests. But right now, we looked at comparison test as an entity, and we looked at the limit comparison tests. Okay, I hope you guys can try problems and be